Okay, I'm going to give you a little bit of a break here. We've already proved Theorem 310 and Corollary 311, and in the proof of Corollary 311, I used homework number 35 kind of as justification in the proof. So let's do number 35. It basically says if you have a non-empty compact set, so E is not the empty set and E is compact, then E is bounded and the supremum of E is contained in E and the infimum of E is contained in E. So the least upper bound of E is inside of E and the greatest lower bound of E is inside of E. When that's the case, we can, if we wanted to, we could use the word max and min. It actually has a value in the set. But in general, as I showed in the previous video, if we take this interval from 0 to 1 on the number line, maybe I'll just write it out as 0, 1. This is not a compact set. It's not closed and bounded. It does not contain its supremum or its infimum. The supremum, the least upper bound, is the number 1, which is not in this set. The greatest lower bound, or the infimum, is equal to 0, which is not in this set. But just like we did in the previous video, this is a closed and bounded set. Its maximum is the number 1. Its minimum is the number 0. Both of those, I should have said, the supremum and infimum are both contained in this set because it's closed and bounded. It's compact. Well, the proof will be about 4 sentences or so, and it's not really doing much math. It's just relying upon other work that we've already done. Okay, E is compact and it's not empty. That implies that E is bounded and the supremum and infimum are contained in the set. This we get for free. Proof, or answer to number 35. Compact implies bounded. So we're done with this part of it. So now we just need to prove that if E is non-empty and compact, it contains its supremum and its infimum. Okay, going back to chapter 0, I believe, every non-empty, bounded set has an infimum and supremum. Doesn't matter what the set is, as long as it's not empty set and it's bounded, it has a greatest lower bound and a least upper bound. So I'll go ahead and just say, so the infimum of, what is the set E? It's E. The infimum of E and the supremum of E exist, or I'll say they are defined, because the set is bounded, non-empty and bounded. Well, I have to refer to another homework problem that you've done. I believe, yeah, you've already done this one. By homework number 22, that was in chapter 1, we know that each of the infimum of E and supremum of E, each one of them is either contained in E or is an accumulation point of E. Well, if they were both in E, we'd be done. So for the remainder of the proof, we're going to assume that neither one of them is, well, we're going to assume that it's not proven for an accumulation point. So we'll kind of assume that, yeah, let's just assume it's an accumulation point of E. All right, so since compact implies closed, well, what does that mean? Well, closed means all of the accumulation points of E are contained in E. E contains all of its accumulation points. And we're pretty much done. Therefore, infimum of E is contained in E, and the supremum of E is contained in E. And that's all we needed to prove.